All right, so this is the last problem on that set of problems I included on the fifth worksheet. So this is a equation of the following form: y double prime is equal to x plus y prime quantity squared, and we want to solve this differential equation. This is a reducible second order equation. With no y terms. And so what that means, if you notice, we've got y prime, y double prime, but we actually don't have the dependent variable y anywhere in this differential equation. So there's actually a sort of similar type of problem where we have no x terms, and that type of a solution was on a previous worksheet. However, the way we can tackle this problem is very similar. And so to do this, we actually just use a substitution. Where we let p equal y prime. And so if we do this, then dp dx, or maybe p prime, is actually just equal then to y double prime. And so why do we do the solution? Well, or why do we do the substitution? Well, it kind of transforms this into something that we're a little more used to looking at. So doing this, we get that p prime is equal to x plus p quantity squared, where here p prime is just dp dx. And so we want to solve this. This is actually a little tricky to solve. So if you expand the right-hand side of this equation, p squared. So I might be wrong, and I might be missing something. I don't think the techniques we've discussed, at least some of the more standard techniques, would solve this. So the way I would solve this, and if you have an easier way of doing it, by all means let me know, is actually to make one more substitution here. So we actually don't need this expanded version. So to solve this, I'm going to let, we'll call the variable v equal x plus p. So what we can do then, if we differentiate this with respect to x, we get that dv dx is equal to 1 plus dp dx. And so now with this second substitution, we know that p prime is equal now to dv dx minus 1. So p prime was dp dx, we just subtract 1 over. And this is equal to v squared. So now this is actually just a separable differential equation. What we can do is we can add 1, divide, and we get that dv over 1 plus v squared is equal to dx. Well, now we just integrate. Here we're going to have a few more steps, but the left-hand side of this, we get the arctan of v is equal to x plus c. And so we can solve for v now. We get that v is equal to the tangent of x plus c. Well, now we made two substitutions to get here. So we'll have to make two more substitutions to get this back in terms of x and y. So first thing we can do Well, v was equal to x plus p, so this means that x plus p is equal to the tangent of x plus c. And so p is equal to tan x plus c minus x. But what was p? P was equal to dy dx, or y prime. But now we just got this sort of in a form that we can integrate. Because we got y prime is equal to tangent x plus c minus x. So now integrate one more time. The integral of tangent is the natural log of secant. You can do that with a u substitution. That actually looks really similar to a cotangent problem we did in the first problem of this. So I'd recommend looking that, going back to the first problem of this sheet and looking at how we did cotangent if you want a little more review on this integral. But for now, y is equal to the natural log of the secant of x plus c. Minus x squared over 2. And so here we actually do need a second constant to account for the fact that we now integrated again. And so I'll just call that constant d. And so that would be the final answer to this, and we get a nice explicit solution. So remember this substitution. I think this was another one of those that, like, the first time I saw it, I really wasn't sure what to do, but this substitution kind of nicely will deal with this differential equation. So if you've got something of the form dy dx is equal to quantity x plus y squared, you should be able to make this substitution and kind of work it through. So yeah, that would be a reducible second order example.